Hello. So in this video, I'm going to introduce Euler's constant E. And I'll go ahead and say what our ultimate goal is here. Even if it's not immediately obvious why we would want to do this. Our goal is to have a function such that the function equals its own derivative. And for the moment, you're just going to have to accept that this goal is worthwhile and that there are reasons we would want such a function. Well, it turns out that exponential functions can have this property, or rather, it turns out that one exponential function has this property. If we have b to the power of x, of course, the derivative of this depends on b. 2 to the power of x and 3 to the power of x and 1/2 to the power of x have different rates of change. So let's see if we can find a b such that the derivative of b to the power of x equals b to the power of x. And I'm going to go back to the limit here. The limit, as h approaches 0, of b of x plus h minus b of x, all divided by h. My goal is for this to be b to the power of x. Working with the left-hand side of the limit, b of x plus h is b of x times b of h. And we can pull a b of x out. We've got a b of x in front of the b of h, and then we've got a b of x by itself. And that gives us b of h minus 1 all divided by h. And again, our goal is for this to be b of x. Well, b of x doesn't depend on h. So, if we look at what we have here, we've got b of x times b of h minus 1 over h. If b of h minus 1 over h would converge to 1 for us, our goal would be satisfied. B of x times 1 does equal b of x. Let's go to Desmos. And let's take a look at b of h minus 1 divided by h. And let's look at what happens as h approaches 0. So here in the graph, h is our variable, and h approaches 0 as we go to the y-axis. And predictably, what happens as h approaches 0 depends on b. So here we're looking at b equals 1.32. And as h approaches 0, this fraction is approaching something like 0.278. Well, or 0.277 or something like that. And this 1.32 is clearly not giving us what we want. We want this to be approaching 1. Well, I slide B up, and you see now when B is 2.44, as h approaches 0, y is approaching like 0.89 something. So increasing b, too far, but increasing b is making the limit get closer to 1. And if we increase b to about 2.71, it looks like the limit is about 1. It looks like the limit is about what we want it to be. If b is about 2.718, then we have the result we want. The derivative of b to the x equals b to the x. And I use the word about there. We give this special value of b a name. We call it E, Euler's constant, one of the great mathematicians, Euler. And this is an infinite, non-repeating decimal. So not exactly 2.718, but about that. And E is the unique number such that, I'm now kind of repeating myself, but the derivative of e to the x equals e to the x. And I'm looking ahead here because we don't take the derivative of exponential functions until a later section. But it's sort of hard to introduce e without talking about the derivative because this is what e is for. The fact that e to the x is its own derivative is exactly what makes e important. So even if we're getting a little ahead of ourselves, it's hard to really introduce it without mentioning that fact.